Thank you, Professor Cohen, for the very kind introduction. Good afternoon, ladies and gentlemen. It is my honor to be here as the last speaker of 25th anniversary of HKUST. And I'd like to thank Professor Kevin Chen and the President Tony Chen for giving me these opportunities. Thank you so much. So today I'd like to talk about how the blue LEDs or deep UV LEDs and the RF devices are developed. And I'd like to explain the future, the vision of this material. But before starting the talk, maybe it is better to start. Where is Nagoya? Maybe no one knows where is Nagoya. It's just halfway between Tokyo and Kyoto. There is a very good or famous castle in Nagoya, but no one is interested because it is made of concrete, not wood. The Nagoya, Greater Nagoya is famous for the industrial city. It's the 20th in the world GDP ranking. It's a little bit lower than Switzerland, but a little bit higher than Poland. Okay. Nagoya University is known as the 7th national university in Japan. The total student population is 16,000. And the international student is more than 10%. Yeah, as Professor Cohen mentioned, I had a very unexpected experience in 2014. So I'd like to talk a little bit about the story. Okay. First, I would like to say that life is unpredictable. Okay. He's very famous. He's my supervisor when I was a student, Professor Isamu Kasaki. Okay. He's also very extremely famous. All the nitride researchers know him, Professor Shuji Nakamura. But I'm the nameless. Okay. So to tell the truth, the Professor Kasaki was nominated more than 10 years before 2014. It started from the early 2000s. So when the October comes, the many Japanese TV staff and their newspaper staff came to our university and wait for the announcement. And I was asked by one of the staff that when Professor Kasaki received the Nobel Prize, the TV staff request me, the comments. So I'm waiting with the comments of Professor Kasaki. So I enjoyed such a situation pretty much. But 3 years, 5 years, and 7 years, it's just the same situation. So I was a little bit tired of this situation. And I decided to go abroad without informing to the university. It's October 7th, 2014. I was in flight from the Nagoya to Frankfurt. The Frankfurt was the transit. And then I opened my PC and found I got many emails. Yeah, entitled, "Congratulations," or "Omedetou gozaimasu" in Japanese. But no one wrote why it is so. So I couldn't understand the situation and went to, oh, sorry. Oh. I went to the Lyon final destination and found many Japanese journalists are waiting for someone. So I tried to go through. And then one of the person came to me and said, "Are you Mr. Amano?" Do you know what's happened? You got the Nobel Prize. I was so astonished. But the problem happened in Nagoya University. I did not inform where I was going. So I was missing at the press conference in Nagoya University in October 7th. Then the next day, October 8th, I was asked to comment on the impression about receiving the prize, but I could not remember what I talked at Minatech. I visited Minatech. I was still astonished, and I could not understand what had happened. There only one thing I could remember on October 8th. That is, one of the trustees of Nagoya University found where I was. And the Professor Kunieda, one of the trustees, called me and said, "You went to France by economy class flight. But return flight, you should use the business class." That's the only thing I could remember when I was in October 8th. And then I returned to Nagoya October 10th, the Friday. The many Nagoya University staff welcomed me pretty much. I was so happy. And the next day, the Saturday, October 11th, there was a wedding ceremony of my former student at Sendai. So we celebrated each other. Then I returned on Sunday, October 12th, and found many, many emails. To tell the truth, at this time, I never contacted with the Nobel Foundation. And I found the email from the Nobel Foundation, and it claims that the Nobel Foundation tried to contact you or me by telephone and by email, but you never responded us. If you never responded us, there might be a possibility of cancellation of the world order. So I was so astonished and tried to call, but they never responded me. So I was figured. But soon I understood that, oh, it's on Sunday. Okay? So I waited until in the morning on Monday, October 13th, and called again. But there is no response. You know the reason? Yeah. There is a time lag between the Sweden and Japan. It's 7 hours. So then I wait until the 5 p.m., then call it. Then there's a response from the Nobel Foundation. This is my funny story. Okay. Yeah. According to the Nobel Foundation, the LED lamp holds great promise for increasing quality of life for over 1.5 billion people around the world who lack access to electricity grids. Due to low power requirements, it can be powered by cheap local solar power. And the LED lamps not only changes our life, but also keeping the traditional lifestyle. For example, the Mongolian young people. Okay? Mr. Gantumul, the Minister of Education and Science of Mongolia, visited us in 2015. He said that the LED lamps keeps the traditional lifestyle of Mongolian young people. The Mongolian people, the nomad life is the normal life. So they do not have the fixed housing. But due to the difficulty in enjoying the TV or the reading the books, the young Mongolian want to have the fixed housing. But the emergence of LED lamps changed the mind of young Mongolians. So I visited one of the family of the Mongolia who keeps the traditional lifestyle, the nomad life. It's a girl, it's like a tent. And inside the girl, I saw that there is really the LED lamps. I was so happy to see that. So what I learned from the natural research, for me, it's a challenge to overcome the common knowledge. This is the history of the development of LEDs. The first commercial LEDs was given by Professor Hiroshi group in 1962. The material is gallium arsenide phosphide. It's a LED LEDs. And in the early 1970s, the green LEDs was developed. It's based on the gallium and the phosphide. Then, if you imagine the periodic table of the element, it's very easy. What is next? Okay? The gallium arsenide for red, gallium phosphide for green. So next should be the gallium nitride for blue. So in 1970s, many world top researchers tried to commercialize the blue LEDs based on gallium nitride, but all the efforts were failed in the 1970s. The reason is we couldn't get the good gallium nitride crystals, we couldn't get P-type, and we couldn't get indium gallium nitride. So many people, or many researchers abandoned these materials. Only one person could not abandon this material. My supervisor, Professor Isamu Kasaki. He wanted to continue the research at the private companies. But unfortunately, the manager of private companies decided to quit the program. So he had to move from the private company to National University in 1981. And I joined his group as the undergraduate student in 1982. When I saw the graduation research subject nitride-based blue LED, I was so impressed. The reason is, at that time, I was interested in computer or microcomputer system. Now it's a PC. Okay? Yeah, in the PC, all the displays, the brown tube was used, which is too big. So if I could achieve blue LEDs, I would change the PCs, or I would change the world. That's the reason why I was interested in the blue LEDs. Okay. For me, Professor Kasaki is like a compass in the ship. Okay. He had the long experience of the nitride. From 1973, he tried the molecular beam epitaxy and found that it is impossible to realize the blue LEDs. Then he changed to hydride vapor phase epitaxy for 4 years and found that it is also difficult. Then he decided to use metal organic vapor phase epitaxy, which is much easier to control. So we, the students, try to start the MOVP growth of gallium nitride. But the problem is, you know that the MOVP reactor itself is very expensive. It's more than $1 million US. But the research funding of the university at that time is only $30,000 US. So we couldn't buy the reactor. So we, the student, decide to develop our own unique MOVP reactor. This is world's only one reactor which is developed by ourselves. The beer bottle. Beer bottle is very important. Okay? We use the RF heating system, but the coil is very, oh, sorry. the coil is very expensive, so we bought the straight copper tube and heating it and winding it to the beer bottle, and then we can fabricate very nice RF coils. Then in such a way, we started the crystal growth of gallium nitride. Yeah, it's a very severe common knowledge. The direct reaction, we could not get the gallium nitride. We need a very high pressure and high temperature. It is almost impossible to realize. So we have to use the foreign material as the substrate. The sapphire is used, but the lattice mismatch is very large, 16%. In general, it should be less than 1%. So this is the common knowledge. We could not get the high quality gallium nitride crystals. So I tried to overcome this common knowledge for 3 years without any success. Okay. So after 3 years of sustained efforts, we could overcome the first common knowledge. I decided to use the buffer layer. The idea came from the discussion with the young professor. Professor Sawaki, he mentioned that in case of boron phosphide on silicon, the phosphorus atom acts as a nucleation center. So the supply of phosphorus atoms sometimes leads to the high quality boron phosphide crystals on silicon. Then I apply the low temperature aluminum nitride as a buffer layer. So we succeeded from the first experiment, the world's highest quality gallium nitride on a sapphire substrate at that time. I was so excited and wrote the patent and also wrote the journal papers, which is very soon accepted for publication. I thought this paper should take notice of many, many researchers in the world, but unfortunately, it is my mistake. This paper did not take notice of other researchers. The reason is, this time, many researchers already abandoned this material and concentrated on other materials like zinc selenide. So for us, it's a very good situation. There's no rival, strong rival. So we could concentrate on this material and then try to overcome the next common knowledge. That is the P-type gallium nitride. At that time, there was the common knowledge, that is the self-compensation. The self-compensation means that when we dope acceptor, it forms a negative charge. Then automatically the defects like nitrogen vacancy is automatically generated, so which compensate the acceptor. That's the concept of self-compensation. So no one believed that the P-type gallium nitride can be realized. But I could not. I could not accept this idea. My impression of self-compensation was only a poor excuse of a non-completion of P-type. I was wrong. Okay? This concept is true. And self-compensation is still one of the hottest topics. But at that time, I could not accept this idea. So during the doctoral courses, 3 years, I concentrated on trying to realize a P-type gallium nitride without any success. But after 4 years of efforts, we finally realized P-type gallium nitride. I changed the acceptor from zinc to magnesium, and I used the low energy electron beam irradiation treatment. Okay, to tell the truth, the emission of first PN diode was too weak. So Professor Akasaki could not recognize emission, even in the dark room. We, the young people, okay, me or the Mr. Kito at the time, the master course student, can recognize the emission. But Professor Akasaki could not recognize. The reason is very simple. The eye sensitivity of a human shift from shorter wavelengths to longer wavelengths with the age. Okay? So the first emission was the near UV emission. So young people like me could recognize. But unfortunately, Professor Akasaki is a little bit elder person. So after several trials, we realized the bright emission which can be recognized even in the illuminated room. Then I wrote the paper and got the PhD. Okay, so how blue LED affect the human life? Yeah, I'd like to emphasize, especially to the young people, the reason why you can enjoy the Game Boy or the Pokemon Go is because of the emergence of the blue LEDs. Yeah, some people claim about the blue light effect. Okay? The mechanism is very clear. The melatonin secretion is suppressed by the strong blue light. So, but it depends on the age, okay? The person who the aged below 30 or 40, maybe you should be careful. But the elder person may not be so serious, okay? But there is a very interesting report from the Japanese researchers. Yeah, maybe many of you have the nearsightedness problem. Okay? You are using the glass. Okay? But the Keio University Professor Tsubota mentioned that maybe near UV light will recover or will suppress the nearsightedness. Okay? So in the daytime, you can use the blue white or the white excited by blue LEDs, but at home or in the evening, you should use the near UV excited white. That's a new story. This is confirmed by the chick. It's a young bird, not by the human. But maybe in the very near future, it will be clarified. Okay? So the LED lamps is contributing to the solving or partially solving the energy shortage or energy scarcity. In Japan, maybe by year 2020, about 3/4 of the LED lamp of the general lighting system will be replaced to LED lamp system, by which we can save about 7% of the total electricity consumption, which corresponds to 1 trillion Japanese yen. That's the blue LED stories. Next, I'd like to explain the deep UV LED stories. Yeah, the Earth is the water planet, but the percentage of the water we can use is very, very limited, okay? The rivers, it's only 2 ppm. And the fresh lakes water, it's 70%. And according to UNICEF, still more than 660 million people lack access to improved drinking water sources, and 2.4 billion people do not use an improved sanitation facility. And global warming causes increase of bacterium in drinking water. So I need the research fund. How to get? We applied to the Japan Society for the Promotion of Science. Very, very happy I could get the research fund, or fundamental research fund, but it's not sufficient. Then I asked the MVP reactor company to support us. Then we could get our unique high temperature reactors, which is the HKUST. And we also need a high temperature spare parts, which is made by tantalum carbide. But tantalum carbide is also very, very expensive. Then I asked the Eviden, another private company. They supported with free of charge the tantalum carbide spare parts. Then we could continue the research. Then we get the next step, the Applied Research Fund from the NEDO, the New Energy and Industry Technology Development Organization, and we successfully fabricate the manufacturing technology for deep UV LEDs. Then the next step is funded by the private bank for private company. And now the Nikiso, one of the private company, start the commercialization of the water purification system using the deep UV LEDs. And these deep UV LEDs can be used not only for purifying the water, but also can be used as a sterilizer, resin cure, the UV curing of the big printer, and also the paper money discrimination and their photolithography. And it can be used also for skin disease treatment. It's a dermatology. So what's next? It's an gallium nitride for RF and power devices. He's the world's leader of the gallium nitride-based device, power device, and RF device. Okay, I'd like to explain about the history of this, the gallium nitride-based HEMT structure, high electron mobility transistor structures. The reason why the nitride HEMT is superior to other materials is because we don't need to dope impurities to the barrier layers. This is the spontaneous and piezoelectric polarization, which causes the two-dimensional electron gas. In case of, for example, gallium arsenide, we need to dope silicon to the barrier layers. So if we try to fabricate high power, high current devices, these low mobility channels causes the serious effect on the device. So that's the reason why nitride HEMT is very, very promising. Okay? This heterostructure started from the Professor Asif Khan. At that time, he was involved in the APA optics. In 1992, he succeeded to fabricate this structure. But he only grew this structure. The process was done at Cornell University, Professor Eastman and Dr. Jin-Wook Baum. But unfortunately, the APA optics did not allow or permit the co-authors of the Cornell groups. So the Cornell groups asked us or proposed us to grow this kind of structure. Okay? In 1995, we focused on the fabricating the laser diode, the blue-ray laser diode. So growing this kind of structure is very easy for us. It's like a piece of cake. So we grew this structure and sent it to Cornell team. Then they fabricated the world's highest performance, the hem structure at that time. But I was wondering, the seed carrier density, 7 times 10 to the 12, it should be too large. So at the initial stage, I couldn't understand the reason. But soon I understood the reason. That is caused by the polarization of these materials, which is clarified or understood. And many people accept these ideas. The origin of the two-dimensional gas is caused by the polarization of this material. Okay, what should we do next? The reduction of wasted energy consumption is the first priority issue, especially for the people living in highly populated countries such as Japan and maybe Hong Kong is similar. So how to realize? According to Hitachi, the lighting electricity is only 14% consumption. Air conditioning and refrigerator is much larger. It's close to 60%. And for inverter control of the motor, Japan is one of the top countries. The inverter ratio is already 100% in Japan. For example, the United States, it's only 11%. Okay? But still, there is a problem. Inverter can be used for solar panels or electric vehicle. The efficiency is, in average, 95%, which is very high. But we have to use many inverter and converter circuits from this electricity source to the final systems. For example, if we use the solar panels to drive a PC, we need a power conditioner. We lose 5.5%. And we have the switching power supply, the AC adapter. We lose 7%. And inside the PC, we lose, in the DC-DC converter, it's 5% and 12%. And finally, we lose about a quarter of the power supply. It's like a remittance charge of bank transfer. Okay. So why gallium nitride or nitrides are promising? The breakdown field is 10 times higher or even 40 times higher than the conventional silicon. So we can reduce the size 1/10. So the loss is 1/10. So by replacing the silicon-based IGBT, we can reduce the electricity consumption by 9.8%. That's our estimate. So what's our strategy? We are trying to develop a gun-on-gun technology. It's the gallium nitride substrate. By changing the gallium nitride on sapphire, which have a lot of dislocations, we can expect the high quality gallium nitride devices if we use the gallium nitride substrate. And recently, our group succeeded the 7-inch gallium nitride freestanding substrate, which is supported by the Ministry of Environment. Then also, gallium nitride is most suitable material for 5G and post-5G wireless communication system because only the gallium nitride can be operated at frequency higher than 100 gigahertz. So we are drawing the future society based on gallium nitride devices. Environmentally friendly society, energy-saving society, and smart society with security, safety, comfort, and convenient. So we, Nagoya University, established a Center for Integrated Research for Future Electronics. We call it the SILFE. So we sincerely hope that the SILFE would like to start collaboration with HKUST for establishing sustainable smart world. And this is our colleagues. Thank you so much for your kind attention.